All right, here we go. So, chapter 11, we're talking about the chi-square distribution. It might look like chi, but it's not. It's chi, okay? The symbol is a cursive looking X with a square. Okay, so chi-square distribution, my advanced bio, AP bio, I don't know what it's called now, but my bio kids, you guys learned this, all right? So chi-squared has its own chart. I gave you the chart packet. I'll teach you how to do, there's a calculator shortcut as well, just like norm CDF, TCDF, all that stuff, all right? A couple big things. It's literally numbers being squared, so we're always going to have positives. So the curve I put here, can be, your values can be 0 all the way up to infinity. So 0 is not in the middle anymore. 0 is on the left, positive infinity is on the right, and since it's a squared value, it's always positive, we're always going to have a right-tailed test, so you don't have to think about which way it's going to be. Okay, my English majors, my grammar people are about to cringe because the first type of chi-squared test we have is called a goodness of fit test. I know, it's awful. So it's the same way as saying how well does our data fit the distribution that we think it's going to fit. The example I usually give is high school. You know, we should have 25% freshmen, 25% sophomores, 25% juniors, 25% seniors. So if we take our high school and compare it, is the breakdown close enough? It's never going to be a perfect 25, 25, 25, 25. But is it going to be close enough that it'll work? Or is it far enough apart that one of the grades isn't the 25%? And then it wouldn't work. Okay, and that's kind of how we're going to look at it. Our formula, of course, is on our formula card. Here it is. All right. O stands for the observed value, and E stands for the expected value. So observed is what's in the sample. Expected is what we expect to happen in our sample. Okay, we're going to see if they're close together or not. Our degrees of freedom for the chi-squared chart is going to be your number of categories minus 1. So that example that I gave you for the high school, there'd be 4 grades in the high school, and we'd subtract 1. Now, it doesn't have to be that they're all equal, right? So if you think about running a race, typically there's not very many 80, 90-year-olds who run marathons, and there's going to be a whole lot of people who are younger. You know, most of the bulk is going to be in your 20s, 30s, maybe 40s, and then it's going to, you know, taper off, and there's maybe 1% of marathon runners are going to be in their 80s and 90s. So we could take a sample of runners from a marathon and see if it matches the breakdown of what we expected. Maybe we expect 30% of the runners to be in their 20s, 30% to be in their 30s, 20% to be in their 40s, and blah, blah, blah. You know, get the rest of the percent. You have to have 100%, of course. And then once you get there, then you can check them. Like, do they actually come close to each other, or do they not come close to each other, all right? And then we would go and make our conclusion. I gave you your condition for performing a chi-square goodness of fit. All right, we still have to check random. Of course, we still have to do our 10% check. But then our last one, our large counts, this one's different. We need to make sure that all expected values or all expected counts are at least 5. All right, and you have to list them somewhere in your answer. You can't just say they're 5 without ever writing them down. You have to show where they are 5. This is the end of the page, so this is a great time to stop. I'm going to go through and do 2 more problems for you guys so you can see them. All right, bye.